string theory. And at least personally, I think there are good motivations to address these sort of questions, given that on the one hand, we know that generalized global symmetries are extremely useful in analyzing quantum field theories in a variety of situations and dimensions. And on the other hand, string theory is an equally powerful tool to create and study several quantum field theories that would be quite hard to analyze by different means. And therefore, I believe it's quite natural to combine these two approaches. And one of the important goals that I have in mind is to try and construct as many controlled examples as possible in such a way that we can hopefully learn important, deep lessons about what the dynamical implications of generalized global symmetries are in quantum field theory in general. And as it has already been reviewed in an excellent way in the talks on Monday by Sakura and Jonathan, and also appeared in various talks today, the modern point of view on global symmetries is essentially topological. We should think of them as a topological subsector, and we have seen in several iterations the appearance of these topological defects that act on operators of various dimensions and have non-trivial fusion rules. And of course, why do we care about all of this? Because this new kind of global symmetries share many features in common with ordinary symmetries. And here I'm just listing a few examples. And of course, they organize the spectrum of operators. Now, there can be local operators, lines, local operators that end lines, and all sorts of things. They constrain the correlators of these objects. They can undergo spontaneous symmetry breaking, for instance, one from symmetries and confinement. And I would guess most importantly for my talk, they can exhibit non-trivial Hooft anomalies that have to match across, for instance, RG flows. This is a point that was already mentioned earlier today in Michele's talk. The thing I would like to emphasize is precisely this D+1 dimensional perspective that Michele mentioned briefly earlier today. And namely, I would like to convince you that it is convenient to attach an auxiliary field theory in one dimension higher to the model that you're actually interested in studying. So I will use curly T for the D-dimensional quantum field theory that we want to study. It might be a Lagrangian theory, a non-Lagrangian theory. It might be intrinsically strongly coupled. That's not a problem. To that, we attach this auxiliary curly A theory in one dimension higher, and we call it the symmetry field theory of the original curly T. And why should we care about something like this? Well, it turns out that this object knows two important pieces of information about the quantum field theory we want to study. On the one hand, it encodes the Hooft anomalies for the global symmetries of our theory, ordinary and generalized. And on the other hand, it also knows about more subtle phenomena, such as, for instance, the global structure of the theory, precisely the sort of questions that appeared in the previous talk by Miriam, for example. And maybe let me emphasize once again, on the one hand, the definition and the concept of this auxiliary symmetry field theory does not rely on a Lagrangian formulation. And indeed, that's also what makes it powerful and interesting in combination with techniques inspired by string theory. And precisely, in string theory, we change the paradigm. We are not talking necessarily about a collection of fields with some Lagrangians, some interactions. We can do that sometimes, and it's very useful. But in a sense, we are thinking about QFTs in a different way, in a more geometric way. The rule of the game is to specify a string background. It could consist maybe of purely a singular geometry, for instance, as discussed by Sakura on Monday, or it could include branes, or even a combination of these ingredients. And I believe that in this context, there is a very natural and pressing question that we have, and namely, given that we are dealing with quantum field theories that are defined in a geometric way, can we compute the symmetry field theory in an equally geometric and systematic way using the same sort of input that defines the QFT itself? And what I would like to, the message I would like to convey today is that there are strong indications that this sort of endeavor is possible in a wide range of cases. And roughly speaking, there is a common theme that emerges, that we can say that the theory that we would like to study, the one that we engineer in string theory, in a sense can be regarded as an edge mode in supergravity. Here, with this terminology, I'm thinking that the localized quantum field theory degrees of freedom live at what is a brane or a singularity in an ambient space that at low energies is described by a supergravity model. And these degrees of freedom, in a sense, leave an imprint in the ambient space. And by studying what happens around these localized modes, we can learn valuable information about what happens at the core. This is an idea that has already appeared in Iñaki's talk in the context, for instance, of S-duality in field theory. And the main advantage of this point of view is that oftentimes we can do a semi-classical computation in the supergravity ambient space instead of doing a computation about the quantum dynamics at the core, which might be very hard and completely beyond our computational techniques. And maybe all of this sounds reminiscent of holography, and it has indeed strong connections given that we can consider branes. But I would like to emphasize that, in a sense, it's logically distinct. And indeed, this logic can also be applied if there are no branes. There is purely a singular geometry, and we will see an example later on. So given that this is somehow the general philosophy, I gave you a short motivation and, in a sense, the punchline. And after this, I would like to spend some time in the second part giving some more general motivations for what this symmetry field theory is, what it does for us, and why we should care about it. And after that, in the third part, I would like to switch gears and talk about the connection between this gadget and string theory. Of course, there would be many, many examples to study. I would like to focus on just two cases. One has to do with wrapped branes, so it's more holographic, if you wish, in flavor, and the other, it's sort of the opposite. No branes at all, just singular geometry, and in particular, I'll focus on the same class of geometries that Sakura has nicely introduced for us on Monday, and then I'll come to some conclusions. Okay, so what is a symmetry field theory? Why should we care? Well, probably, of course, in this audience, I don't have to spend a lot of time recalling what a Hooft anomaly is, but just to sort of set my notation and terminology so that we're all on the same page. The main object of interest is a quantum field theory, of course, without dynamical gravity, our curly T, and we suppose that it has some global symmetry, and therefore we can couple it to some background for that very schematically I'm denoting with A. And the idea, of course, of a Hooft anomaly is that if we do a background gauge transformation, our partition function doesn't quite go back to itself, and we cannot cure this by some sort of counter term. In other words, we could say that the partition function is not quite a function in the space of background fields, but rather a section of a non-trivial bundle, with the anomalous phase being essentially the phase that we pick up when we change trivializations. Now, this, if you wish, is maybe the more sort of old school approach to anomalies, and of course it's perfectly legitimate, but for the purpose of my talk, I would like to adopt a slightly different point of view, which is physically equivalent, which is based on the following idea. So what we are actually interested in is a d-dimensional quantum field theory, our curly T, and it has a Hooft anomaly. Its partition function per se is not gauge invariant. So let's cure gauge variance by attaching our theory to an auxiliary bulk in one dimension higher, the curly A. And in order to do that in a simple way, let me, for simplicity, assume that we can extend both the space itself and its background fields one dimension higher. So in more technical terms, for simplicity here, I'm assuming that the relevant cobordism obstructions are zero. In this favorable situation, the picture is a bit simpler, and the idea is simply to consider the combined system of our quantum theory curly T combined with this curly A, and to do that in such a way that the failure of gauge invariance of curly T, the Hooft anomaly, is precisely cancelled by an equal and opposite gauge variation in curly A. So at the end, we have a system that is completely gauge invariant, but now generically will depend on the extension. Now, of course, in the process, we don't want to introduce any higher dimensional degrees of freedom or propagating modes or anything of that sort. So that's why curly A will be a topological theory, and the fields that appear in this theory are nothing but the background fields of our original QFT. So that's the kind of object that we would like to consider. And to connect the idea of this theory to the more traditional idea that if you do a gauge transformation, you get an anomalous phase, let me now tell you about this, how to put together these two ideas. And one very important point that I won't have the time to exhibit explicitly, but I want to mention, is that this topological order in one dimension higher, this curly A object, satisfies, it's a bona fide quantum field theory. It satisfies all the axioms in, for instance, the formulation by Segal and Atiyah. And furthermore, in the context of Hooft anomaly, it's an invertible field theory. Now, the technical definition would require to introduce some terminology that we don't need today. All we need to know is that if you take this d+1 dimensional theory curly A and you feed to it a closed manifold, it will give you a non-zero complex number, which is actually a phase. Whereas if you feed it a space that has, it's d+1 dimensional and has a boundary, it will give you a one-dimensional complex vector space as its Hilbert space of states. And now, using the cutting and gluing axioms of QFT, we can recover the original anomalous phase. So let's say, for example, that our spacetime is M, and that we want to study what happens if we perform a global symmetry transformation phi. What we can do, again, provided for simplicity that the appropriate cobordism obstructions vanish, we can realize M as boundary of an auxiliary space U in one dimension higher and glue two copies of U with opposite orientations, but with a non-trivial action of phi in the gluing. And we get a closed manifold in one dimension higher. We feed it to our curly A QFT, and it gives us a number. And that number is precisely the anomalous phase that we would encounter in the traditional formulation if we were to do a gauge transformation in our original d-dimensional theory. And for instance, what about a very familiar Hooft anomaly, maybe the very first one that we learn about, chiral fermions in 4D. Those are the famous triangle diagrams. And we know that we can encode them in an anomaly polynomial using descent. And using this language, at least roughly speaking, we can think of this anomaly theory as being essentially a theory whose action is the Chern-Simons form. This gives us a good intuition. It's not quite mathematically correct. The correct treatment involves the so-called eta invariant, the exponentiated eta invariant, and that's because Dye and Fried showed that it truly satisfies the axioms of a QFT. And not just that, it also captures both perturbative as well as global anomalies related to chiral fermions in 4D all at once. So it's a very powerful tool. So this would be what it's usually referred to as the anomaly theory. But in the title, I mentioned the symmetry field theory. So what's the difference? Essentially, the difference is relatively small. What we relax is the invertibility assumption. And if you relax that, what happens essentially is that now, if you feed your curly A theory a d+1 dimensional space that has a boundary, it will give you back a vector, complex vector space, but that might have a dimension that could be greater than 1. And that, in turn, implies that our physical theory in D dimension doesn't quite have a single partition function on a suitable D-dimensional closed manifold, but rather has a whole vector of these. And this is a phenomenon that is familiar from chiral 2D CFDs and 3D topological field theory, and has famously a direct analog in the context of 6-dimensional to 0 CFDs, for instance. So that's one of the motivations to relax the invertibility assumptions, being able to describe relative field theories that possess a vector of partition functions. Related to this, there is another motivation to relax the invertibility assumption, and namely that if we do so, our friend curly A can also tell us about the global structure of our theory. And by that, I mean that it happens in many examples that two different quantum field theories share the same spectrum of local operators, but happen to have different spectra of extended operators. And therefore, they have different generalized global symmetries. And curly A can tell us what's going on. And of course, here, the prototypical example I have in mind is that of a gauge theory, for instance, in 4 dimensions. If we pick two different, say, gauge groups based on the same gauge algebra, of course, the local operators are going to be the same, but they have different lines. That's precisely the sort of question that was also addressed by Miriam in the previous talk. So here comes, in a sense, the picture that summarizes what's going on. It has already appeared, I think, briefly this morning in Michele's talk. So this is, in a sense, the most general situation we should have in mind. The theory we're interested in is curly T, which might be a relative quantum field theory, relative to this curly A gadget, the non-invertible symmetry field theory. Now, let's say that we want to choose, for instance, a global form of gauge group. That corresponds to choosing a gapped interface, which would be this red line in the picture. And what we have on the other side, it might be nothing, might be trivial, or there could be a remnant invertible field theory that now encodes just the Hooft anomalies. And in a sense, now, since everything is topological, we can imagine to take the red gapped interface and collide it with our non-trivial quantum theory T, and then what we would get is an absolute quantum field theory with, attached to it, its invertible anomaly theory. Okay. Maybe like this notion of a non-invertible topological quantum field theory might sound a bit strange or unusual, but there is actually a very simple example that I would like to discuss briefly that I'm sure most of you have seen in some form or another. Namely, let's consider, let's say that we want to study a 4-dimensional theory so that our auxiliary theory lives in 5 dimensions. So let's consider this specific topological theory in 5D. Well, clearly it's a Lagrangian theory, since I'm writing down an action, and the fields are two-form fields. And even though I'm writing it in terms of continuous p-form fields, what actually happens by virtue of the equations of motion is that this 5-dimensional theory is describing a discrete gauge theory in 5 dimensions. In particular, both B2 and C2 are flat, and they have holonomies that must lie within a Zn subgroup of U1, where n is the coefficient in front of the action. Now, there are no non-trivial local operators, essentially because the field strengths are 0, but there are, for instance, Wilson surfaces. Here, I'm writing one for B that has a charge little n, which is only defined mod Zn. And of course, you can also consider the analog for C2 or a mixture of the two. And the main claim that I want to make, or just mention, is that this topological field theory is indeed not an invertible theory. And in order to detect this, following, for instance, the analysis of Witten, we can perform, say, a canonical quantization, and since this is a free theory, everything can be, it's subtle, but everything can be studied explicitly. And one finds indeed that if our space-time has a non-trivial H2 with values in Zn, the space of states of this 5-dimensional TFT on that gadget is going to have a basis precisely labeled by those elements. So it can be, and generically will be, not one-dimensional. And so this is a brief reminder of the 5D theory itself. What is the interplay with the 4D gauge theory, for instance, say, SUN gauge algebra? Well, essentially, the idea is that these two guys come together and that, for instance, we can consider a Wilson surface for, say, B2 in the 5D bulk, and that can end on our 4D boundary, and it just becomes, for instance, a Wilson line. And we could play the same game with C2 and get a Hooft line. And our task now is to choose a global form of the gauge group in order to get an absolute theory. And that corresponds to choosing a maximal set of surfaces in the 5D bulk that have trivial correlators with themselves. And this, in turns out to be the same as choosing a topological boundary condition for this 5D theory. So this would be the red line. And here, for instance, here I'm considering a simpler case where after the red line, there is really nothing left. So this is like, it's not really the most general situation, but it gives you an idea and a concrete example. And say, for instance, we want to study global form SUN. All we have to do is choose the Dirichlet boundary conditions for B2, which will give us the desired electric one-form symmetry in 4D, whose background field is precisely the boundary value for B2. So this was a brief reminder, and hopefully I can give you a flavor of this sort of problems if you haven't encountered them before. Now let's switch gears and consider what happens within the context of string theory and how we can derive the symmetry field theory, so essentially the anomalies and the BF terms, in the example of wrapped brains. And clearly, I guess I don't have to convince this audience that it's a good and useful thing to consider quantum field theories, and in particular, say, supersymmetric quantum field theories that originate from M5 brains in various dimensions, 6 and below. And clearly, the prominent example to keep in mind is that of the reduction to 4 dimensions, which can happen on a Riemann surface, most notably with punctures and defects, which fits in the broader class S program in which we start with some 6D CFT, and we obtain a supersymmetric quantum field theory in 4D that can exhibit a rich variety of global symmetries, and also, importantly, it's generically strongly coupled, or non-Lagrange, even though this is could be a time-dependent statement, as we have seen in Iñaki's talk on Monday. In any event, let's consider the case where the parent theory in 6D admits itself a realization in terms of M5 brains. This could just be a stack in smooth space. Of course, this is the 6D20 theory of type A. Or for instance, it could be brains probing a C2 mod gamma singularity so that we have less supersymmetry. When this is the case, namely when the 6D theory itself can be realized in M theory, we can have two different viewpoints on our 4D theory. We can go from 6 to 4, and that's a purely field theoretic construction. Or we can consider it directly from 11 dimensions. And in the second point of view, our task is to use the geometry of the configuration to learn about what sort of global symmetries we have in 4D, what are their Hooft anomalies, what kind of BF terms and global structures we can have, and so on and so forth. And you might wonder, why should we care? It's perfectly reasonable to go from 6 to 4, and indeed, it's a very useful construction. But I would like to point out that it's oftentimes very useful to compare the 6D to 4D point of view to this higher dimensional viewpoint. And I would like to point out two examples. The first essay is class S with punctures. in the absence of punctures, we can take the anomaly polynomial of the parent 6D CFT and integrate it on the Riemann surface. And by virtue of anomaly matching, we get the anomalies of the lower dimensional theory. But if we have punctures, this procedure doesn't quite work as straightforwardly, because essentially there are extra degrees of freedom supported by the punctures, at least intuitively speaking. But if we go back all the way up to 11 dimensions, we can recover, indeed, everything, both the bulk of the Riemann surface as well as the punctures, which could be of regular type or irregular type. And as another example, even if we don't have any puncture at all, say, for instance, we start from this 60-1-0 theory, the one that lives on the M5s probing the singularity. In that instance, there are very subtle decoupling phenomena that happen when we go from 6D to 4D. So in that case, it also turns out to be useful to compare the 6D to 4D to the 11D to 4D approach, because the comparison helps us understand in a more geometric way what's happening in terms of these decoupling modes. And this is something we have studied in a class S2 case study, and we found quite some non-trivial pattern of decoupling, which is essentially explained by the 11D story. So given that I have hopefully convinced you that it can be useful to consider this M-theory perspective on these QFTs, what is the main tool at our disposal to make progress in the analysis of these models? And that's, not surprisingly, anomaly inflow, since in this case we have brain sources. And famously, this was also the first way in which the anomaly polynomial of the 6D to 0 conformal theories was derived. And let me mention that the same inflow analysis actually accounts for global symmetries, for instance, of the 6D to 0 superconformal field theories. Now, I'm not going to discuss global anomalies, but I would like to stress that the same philosophy can be applied essentially in lower dimensions to setups that have wrapped M5 brains in a very systematic and streamlined fashion that can uncover for us both ordinary and generalized symmetries and their anomalies. Now, the whole computation per se, maybe it's not particularly interesting, but I would like to give you an idea of what are the main ingredients involved. So just to set up our notation, let's say that we want to study a d-dimensional theory, so let's say 4D, and that it has a word volume WD. So that's our external spacetime. Then we have all the other directions, but let's think of them as an overall radial coordinate and some compact angular space that surrounds the brains. So in the simplest possible case, the 60-dimensional case, this is just literally a force sphere that surrounds the stack. In general, this internal space, it's supported by the flux, which is sourced by the brains. That's precisely the duality between brains and fluxes that has appeared in a few talks already before. And not surprisingly, if we're thinking holographically, this space that I'm referring to is precisely the internal space that we have in our ADS5 or, say, ADS D+1 solution. So the task that we have is to take this as an input, this compact internal space, supported by some background flux, and turn it into statements about what kind of global symmetries we have and what kind of symmetry field theory they are exhibiting. And first, let's say, what kind of global symmetries can we detect? And there is actually quite a large class of those. And essentially, we can use the isometries, because we know from the general KK paradigm that they will give us zero-form symmetries, potentially non-abelian ones. But we also have internal cycles in the geometry. And if we expand the M-theory 3-form on those, we can get, depending on the details, a whole bunch of P-form fields, and those correspond to P-form global symmetries on the other side. And so that's like enumerating the symmetries we see. What about their anomalies and the symmetry field theory? Well, inflow tells us essentially that they are derived from the topological terms in the low energy effective action of M theory. And as we know, that consists of the two-derivative term, the CGG, that I'm writing here using descent as a 12th form, as G4 cube. But we also need a very important topological higher derivative correction constructed with the Pointryagin classes of the tangent bundle that is needed for the consistency, the quantum consistency of the low energy effective action. And what we were able to find, rephrasing and building on the original inflow analysis, is that there is, as you can see, a completely uniform algorithm to take your favorite wrapped M5 configuration, and starting from a universal 12th form, which is just an avatar of the topological couplings in M theory, and integrating it on our internal space, we get the inflow anomaly polynomial. And that, in turn, is essentially identified with the symmetry field theory of everything that lives on the branes. Now, as a caveat, this everything oftentimes includes both an interacting piece as well as some free decoupled sector that we might want to identify and subtract. I haven't told you what G4 is. Well, of course, it's the G4 of M theory, but in practice, how is that constructed given this philosophy? And in a nutshell, that's nothing but the background flux that is our input dressed with all the background fields that we can turn on. And while the technical details on how this is done are not terribly important, I would like to emphasize that there is indeed a natural connection that emerges with equivariant cohomology. And why is that the case? Well, let's think about the input. The input is our external space-time and the internal space. And if we don't turn on any background fields, we just have a direct product and a background G4 configuration. Now let's say that we turn on the background fields. Effectively, we are fibering our internal space over external space-time. And therefore, G4 bar, which was defined on the fiber, is no longer a well-defined object. In physics terms, we would say that we are gauging something, so we should couple it to Kg vectors. But if we do so, in general, the closure of G4 bar is gone and has to be restored, of course, because G4 must be closed. And by the time the dust settles, what we find is a new form G4 without the bar that contains all the background fields, and that is nothing other than a representative of an equivariant cohomology class, essentially in the Cartan model. And here, equivariant with respect to what, you might ask? The relevant symmetry group, G, is nothing but the isometry group of our internal space. So to showcase the flexibility of this approach, let me tell you something about a specific example that is a case of class S2 theories, which means that as our parent theory in 6D, we choose the one generated by M5s on top of a C2 mod Z2 singularity, and we go down to 4 dimensions without any punctures. We use the standard partial topological twist to preserve supersymmetry, and we also include a flux for the SU2 times SU2 symmetry of the parent theory, which will be broken down to U1 times U1. And what we were able to do is implement this program that I have described in quite some detail. And if we do so, we can access and get very explicit results. Here, I just wanted to flash you the sort of expressions we get. Of course, the details are not important. I don't expect you to follow everything. But just to give you a flavor, for instance, of what kind of global symmetries we can detect, well, we have zero-form symmetries from the isometries of the internal space, as usual, which are essentially a combination of those. Through A maximization will be the R symmetry, but the others are flavor. Then we have, of course, gravity and external space-time. And then there is, as you can see, a whole collection of p-forms that come from non-trivial cycles in our internal geometry. And what kind of terms we get? Well, as you can see, there is a whole variety. Some of them are just Hooft anomalies. So those would be the invertible part of the symmetry field theory, if you wish. And for instance, in this box, I'm highlighting a few mixed anomalies between the various isometries that we can find. But we find more. This is not just an invertible theory. For instance, in this little box there, there is a BF theory hidden, which is of the same type that I discussed earlier, a B2 wedge DC2, or B2 Tweedle. Except that in this specific instance, we have G copies of that, the genus of the Riemann surface. So this gadget controls what would be the analog of the choice of a global form of the gauge group, except that oftentimes these 4D theories don't have a gauge theory description. And it's related to line operators in our theory. But interestingly, that's not the only BF term in the game. There is also another one that has to do with different degrees. In this case, it's a 1 form and a 3 form potential. So this term is telling us two interesting physical phenomena are happening. So the first, as you can see, it's written in terms of a linear combination of three things. It means that we had three putative massless U1s, and one combination of them gets topologically massive and participates into this BF coupling. And then the BF coupling itself is telling us that we have a choice of global form. Do we want a theory with a discrete zero-form symmetry, or in a sense, do we want to gauge that and go to a discrete two-form symmetry? The symmetry field theory knows that we have these options. Okay, so that was a very quick flash of the story with the branes. And now, briefly, let me tell you something about the pure geometry. So here, luckily, I don't really have to introduce this sort of setups in any detail because Sakura did an excellent job in reviewing how taking M theory on a suitable conical Calabi-Yau singularity, we can get non-trivial 5D CFTs. And our goal now is how do we get the symmetry field theory for these models? And the idea is very similar to what we have considered earlier. We have to surround the singularity with a smooth, compact space, which in this case, the thing I'm calling L, is nothing but the base of the cone itself. So for instance, it can be, for a Calabi-Yau threefold cone, this is going to be a Sasaki-Einstein 5 manifold. And morally speaking, since we're dealing with topological objects, we can imagine to sort of deform this cone into a cigar as sort of depicted schematically there. And if you go all the way down, you have this half line, which is reminiscent of this bulk plus boundary picture. This is a heuristic argument, but it's telling us that it's a good idea to essentially perform a dimensional reduction on the link, which is good news because the link is, for isolated singularities, is a completely smooth space, and we can perform this within the supergravity approximation. So the name of the game would be now to take, again, the topological terms of M theory and reduce them on this space, which sounds relatively straightforward, except that there is a technical difficulty. As we have seen in several talks already, we are dealing with discrete symmetries that know about these relative cycles, modulo cycles, which is ultimately linked to the torsion in the link geometry. So what we have to do, in other words, is to do a KK expansion onto torsional cycles. How can we do that? There are various techniques available using p-forms that are not closed in the internal space, but for our purposes, we found it best to use differential cohomology in the way it was, for instance, introduced in physics in the context of non-commutative fluxes. And here, as a word of caution for the experts, I'm refining ordinary cohomology, which ultimately it's probably not going to be the correct thing to do because we know from K-theory that we should use some sort of extraordinary cohomology theory. But for our purposes, this approximation turns out to be good enough. So very briefly, let me go back to an example that Sakura covered already quite in some detail, a very simple Sasaki-Einstein, YPQ. The corresponding 6D CFT can be mass deformed to the gauge theory SUP at level Q. If you look at the cohomology of the link, this Sasaki-Einstein, you will find two objects in H2. One of them is torsional. I'm calling it T2, so it will give you discrete background fields. And this B2 is precisely the background field for a discrete one-form symmetry. But there is also a non-torsional generator, and that will give you an ordinary U1 zero-form symmetry. And now we have to see how these ingredients combine. Our analysis shows that there are two terms reported here schematically. One is a pure cubic anomaly for the one-form symmetry. The other mixes the zero form and the one form. And the anomaly coefficients are defined modulo 1 and are ultimately a suitable refinement of linking pairings of these torsional T2 and the non-torsional V2 that I mentioned earlier. Now you might wonder, how do you actually compute all of this? And there is a systematic way that essentially maps the problem to an intersection problem, and I will be, of course, very happy to tell you more about it in case you're interested. Here, I would just like to highlight that we do find very explicit expressions, and they agree with field theory results when those are available in the literature. But this technique can also be applied to non-Lagrangian models, models that don't admit a description in terms of non-abelian gauge theories. And therefore, it's also something that is telling us something about the CFT point intrinsically. So it's useful also in that regard. And it's useful to compare it to other approaches, such as in the work of Miriam, based on the resolution of the geometry. So to summarize very briefly, I hope I convinced you that the symmetry field theory is a useful object to consider. And I have shown you in two examples that in the context of QFTs that are realized in string theory, there are systematic tools that we have to extract it. And roughly speaking, they're based on the idea of taking the topological couplings of the parent theory and reducing them, in principle including both torsional as well as non-torsional cycles, for instance. And as we have seen, both equivariant and differential cohomologies pop up quite naturally. There are several natural future directions to explore. Of course, those are just very specific examples in the landscape of all constructions. And also, I think it would be interesting, it's interesting to try to combine these two things. And ultimately, I believe that something like equivariant differential cohomology, for instance, should be a unified language to address more questions. And also, let me emphasize, I've been telling you about essentially higher form symmetries, but the world of generalized symmetries, as we know, is much richer. There is the higher groups, the non-invertibles, and I think it would be extremely interesting to try and push these sort of methods to attack those problems as well. Thank you.
Questions for Federico? So when you mentioned the 6D theory going down on a Riemann surface to get a 4D theory, one of the cases that's known to be a little bit tricky to read the anomaly from is if you compactify on, say, a 2 torus, because then all the curvatures vanish, and then you have to use some other technique to sometimes extract the anomalies. So how does this kind of method extend? Does it work in those cases, or if not, what do you do?
Yes, so the question was what happens, say, for instance, for T2 reductions where there is like a singular geometry. Indeed, it's not guaranteed to work. Like, I would say that it's probably the indication that it's best to dualize and say go to another frame. And then in that frame, it should be possible to perform a similar analysis. Even though empirically in some of these class S2 constructions, we see that the M-theory inflow even works in the case of T2, where maybe it wasn't necessarily obvious that it would work. Probably it's the flavor flux that is regularizing the setup.
So that's in the 11-dimensional setup?
Yeah. Oh, I see. No, that's a very interesting idea. I think I have only encountered this sort of slab constructions. So I'm not aware of results in that direction, but that sounds quite interesting. Oh, I see. That's right. Yes, that's an interesting observation, but I don't think I have a good question, a good answer.
Yeah.
At some point you mentioned that the 16,0 theories are relative theories apart from the unit.
Mhm.
Why is that? Is it related to the symmetryless
Um, well, essentially, like it's a special case. There is also no center. It's related to the lattice of charges of string operators. Essentially, you can verify that in that specific instance, this higher dimensional vector of partition function always collapses to be one-dimensional.
Okay, let's thank Federico again.